said that like. He said that you. Okay, there was only one person. No, I don't think he said. I don't think he was
Very last request. During micro
I know. No one did show me you what you got? Did he take
everyone? Interrupt your holiday.
It's
amazing how much more people are here on test day. Should we have a quiz? Sure. You don't have it last time. Okay, so those of you at home, we were kidding about the quiz, but you should be here, you bastards. I don't really know what to say. We're almost done. This is the last week. So I don't quite know what I'm going to go over today. I'm going to go over a couple of random factoids. You know, kind of stuff that you know you should kind of know, but stuff that I don't know. Am I going to put it on the exam or not? I'm going to tell you. I'll tell you, because that sucks otherwise. And then Friday we have a review. And the review is going to be very comprehensive. All right, so you're going to get. I mean, if you haven't figured this out yet, I give a lot of clues during the reviews. Right, so you're going to see a lot of that. Anyway, questions. So again, we have a Friday. We have a review. I'm going to take a little bit of a break in between the 2 hours because I have to catch my voice. And that's kind of hard for me because I'm going to just talk nonstop. And there you go. And then the exam is the exam. Remember, it's on Wednesday. It's from 1 to 3, not 2 to 4. 1 to 3. I don't know why they screw me every year like this. They do this every year. Go from 1 to 3 as opposed to 2 to 4. All right, so don't. All right. And I swear to God. Every year, some stupid jackass walks in at 2 o'clock and is like, what? I'm like, stupid jackass. Anyway, probably one of the people listening to me right now. Anyway, any questions? Questions.
Do you know if it's going to be in here, or if it's going to be just...
No, it's in here. It's in here. Yeah, they did not screw me over to that extent. I mean, it kind of makes sense to have it from 2 to 4, but they're not doing it. And I can't control them. And I keep telling them to not do that, but they won't listen. Any other questions? Are we okay? Okay, now how did Astor go? Okay? Yeah, all right. Yeah, she's your favorite anyway, whatever. I just want to remind you, excuse me, I want to remind you about what she covered, as we do every year. Oh hell. Why don't I just talk about what I did over the weekend? No. Let me go over what Azra went over, and then I'll go over what I did over the weekend, which is I was working at Argonne, which was really awesome. And I'm going to tell you exactly what happened because it was really cool. So anyway, so you have these P versus T diagrams. And again, you know that this slopes one way or the other depending on whether it's water or not. So you know that. We went over that. Okay, now I know that this is a solid, this is a liquid, and this is a gas. Now I figured that out because at low pressure, at high temperature, There's gases. I also know, because I used to work with that guy that used to do the critical phase washing, so that's why I know that this is the critical region. Excuse me, critical region. Anyway, my handwriting's bad today. Anyway, so you can just kind of figure this out logically. And what Azra did was point out to you that if you have a starting point, we'll give you a starting point, then you can figure out the rest of the line. And the way you figure that out is the way that pressure changes with temperature is the change in entropy per mole versus the change in volume per mole. Now, again, this is why water is a weirdo. Now, water's kind of important. I mean, I don't like to teach weirdos, but water's important. Water's important because it's change in volume per mole is negative. And almost nothing does that. Nothing does that except water, but water's everywhere. So anyway, and that ends up being, because we don't have an entropy meter, we've never had an entropy meter, as a result, what we have is a, hopefully Azra pointed it out this way, I don't have the video of that. I'll put up notes shortly. Hopefully that she put it this way, that entropy is delta H over T. All right, so hopefully she put it this way. And from that, I'm not going to go over all the equations. Anyway, you get a whole bunch of equations for how this works. And anyway, so again, I'm just going over what Azra already covered. Okay, so anyway, what I want to go over now is the fact that this is really kind of boring. I mean, it kind of sucks. And I want to make it interesting. It turns out that there's all kinds of different phase transitions. Now, pressure, temperature, whatever. It turns out that there's all kinds of phase transitions, and I want to go over a couple with you. Let me go over two different ones. Magnetism. Okay, so it turns out that there's magnetic phase transitions, and what you have are materials. This is kind of important. Magnetism is very important. What you have is materials that have atomic. Sorry, can't talk today. You have atomic lattices, and they have unpaired spins. That means unpaired electrons, and because of that, they tend to line up. And so let me go over. Magnetism. So what you have, again, are these unpaired electrons, and all these materials like iron are cobalt. I even was looking at Imgur the other day, and they said, oh, iron is the most magnetic of all materials. It's not. It's cobalt. Cobalt is by far more magnetic. And so they have these unpaired electrons, and the electrons line up in such a way that they create magnetism. And that, that means that I can switch on a magnetic field, and I can get it to do the opposite. So, and don't even write this down, by the way. This is like whoop-de-doo. Who cares? All right. The thing was that no one realized, well, you had to go through a different phase to do that. You had to do something like this. And I'm just drawing this at random. So no one write this down. what you have to do is you have to go through this kind of dynamic disordering, or you can't go from here to here. It's technically its own phase. And anyway, it's technically a phase transition, very different than what you're used to here. I mean, this is vanilla. I mean, this is boring as hell. This is kind of cool, because this is how all of your, your USBs work. Basically, all your dynamic memory, everything works this way. It's kind of cool. Now, the reason I bring that up was because this is what's called a ferromagnet. Let me bring up what's called an anti-ferromagnet. Sorry, my handwriting's bad today. Okay, anti-ferromagnet. Now, it's kind of easy to draw everything pointed up, but some things want to be pointed down. And the way that works is like this. Up, down, and then down, up. Okay. Really freaking simple. All right. Now, us chemists, us synthetic chemists, I'm kind of a synthetic chemist, we have all kinds of really cool shit. I shouldn't have said that. We have all kinds of cool shit. And we can make materials do really weird things. Now, here's a way we can do that. Okay, let me draw this. This is very difficult. All right, so again, these are atoms. These are atoms that have excess electrons. The way that works, just like I said, they have excess electrons. And let's see. Hopefully this is not too bad. There we go. Yeah. Okay. Copper does this. Copper loves to get in triangles. Now, let me ask you this. Copper likes to be antiferromagnetic. And that's something you're going to learn in 344. What do I do with this? You see a problem? Anyone? Up, down? Which is it? I can't do anything with it now, can I? If it's up, it hates this one. If it's down, it hates that one. You see? There's nothing you can do with it. It's stuck. Now, what ends up happening as a result is, let me redraw it, hopefully a little bit better. All right, so it's called a spin-frustrated system. Ew. Maybe I didn't draw it as well. What happens is, all right, we think of these magnetic moments as up or down. What they do is they cant inward. You see, there's no solution. So they cancel each other out. And so that there's no option. Right, exactly. That's exactly what they do. They, again, they cancel each other out because there's simply no way to satisfy the spin frustration system. And what that causes is, guess what? What's the word? Well, it's called super paramagnetic behavior, but I mean, I know the technical word. It's when you get superconductivity. And the way that works is, here, let me draw this on the new board. Now, this was a model system discovered at MIT when I was there. And the way it describes is a copper system, which all of you are very well aware of, even if you know it or not. So it turns out that copper is a superconductor. excuse me, you use copper, actually, you know, God, what's the technical term? I'm trying to filter multiple things at once. Anyway, you use copper, essentially insulators. You use copper insulators, and what you do is this. So again, I got copper, and how do I want to draw this? Let me think about this. Up, down, up, down, up. Sorry, I'm not very coherent today. That's up, that's down. All right, what you do is you get copper insulators. And what you do is you punch a hole in it. And you do that chemically, or you do it by, actually, you can do it radioactively, which is kind of scary. Now, think about this. What's the only way to get this guy here? Anyone? Now, I've kind of already given you the answer. Move how many? Move one electron, or move two electrons? Right, you move two electrons. And so this guy has to move with this guy, which simultaneously moves with that guy. All right, that's called a Cooper pair. And that is why things are superconductive, because they have to move in pairs. What happens is that electrons get hot in the wire because they have to move in single file, essentially. But when they have to move in pairs, then all of a sudden they become, like I said, they get this Cooper pair thing going, and they don't have to move with heat. And I even brought this up. I brought it up a long time ago, and if you don't remember, it's not a big deal. It's a quantum thing, and it's called a Bose-Einstein condensate, and you're going to learn about that in 344. That's definitely one of the subjects of 344. So you form these Bose-Einstein condensates, and things move in pairs, and they move without heat. They move without friction. And anyway, that's where superconductivity comes from. So I thought that was kind of cool. Before I get into the next material, because I have plenty of time, I also want to go over what did I do over a break. What did I do? I was at Argonne National Lab, and we discovered a phenomenon that was unprecedented. And you're talking to a famous guy right now, by the way, just so you know. What we did was we took a material, how do I put this? Just so you get used to your quantum mechanics. All right, quantum mechanics says, yeah. God, I'm going to erase that. Quantum mechanics says that you have potentials. Potentials are traps. And I will try to do oh, that's better. Especially if there we go. That's better. All right. Quantum mechanics sets traps. Traps, that's potential. That's potential energy. Potential energy is doing that. And that's what you're going to learn. You have to set the trap. Now, what you get is the kinetic energy. Now, the kinetic energy is such that, actually did that correctly. Kinetic energy says that you have to fit a wave inside of the trap. Potential, trap, kinetic energy. This is everything. This is how quantum mechanics works. Because I'm especially not really willing to go over all the crap I'm supposed to go over. The next thing is, though, excuse me, is that because the wave has to fit, it means that the next wave is like that. Okay, that's a step. Now, do the calculations. That is a step in kinetic energy. Let's do the next one. Let's do the next one. It's like that. Now again, calculate. You'll do it. You're going to do it next semester. And what you find is that there's these steps in energy, in terms of kinetic energy, that you really can't avoid. And it's absolutely true. Now, can I build a trap for, say, an electron or whatever the hell? Can I build that? No, not really. Not. I can't build like some kind of metal void where, you know, there's like some kind of surrounding entrapment. I can't really do that. No, it doesn't really exist. However, what I can do is I can make a quantum dot. Let me write that down. I can make quantum dots. And quantum dots are actually, they're kind of a pseudopotential for the same thing. They're kind of the same, not quite. And what ends up happening is, as you are going to learn, I did a good job. So I have a circular semiconductor. Now the semiconductor, what happens is, man, that's kind of shitty. Anyway, what happens is it absorbs light. And when it absorbs light, as you're going to learn, you're going to have an electron in an excited state. And it's just what semiconductors do. It's kind of important to their function that they do exactly this. Now, here's a funny thing. Something that a college-educated person should know. Semiconductors don't do much. They don't do anything. All right? They need to be doped. This computer contains silicon. No. It contains partially silicon. Silicon is doped, actually, with phosphorus and boron. Phosphorus and boron. If it wasn't doped with phosphorus and boron, it wouldn't do jack diddly squat. And so it's very important to their function that they're doped. So anyway, what happens is, in the case of copper, now, you don't have to write this down, by the way. I'm just saying, this is what I did over the weekend. So, copper plus, if you dope it in a semiconductor, what happens is you shine light on it, and the electron jumps down to the copper dopant, and then the electron jumps down to its resting place, its semiconductor home, essentially. How do I know that? I measured it. Because what we did was we shined light on the semiconductor, and then we shot off the electron with X-ray. Don't even write this down. We shot the electron off with X-ray only because of where it was at. And we could see the electron show up to its home, and then we could see it go away over time. And anyway, I'm going to be famous for this, by the way. So, just so you know. You totally don't care to me. Anyway, all right. So I'm babbling, and anyway, this is what I did over the weekend. This is why I wasn't here on Wednesday. It's because we were making these measurements, and it's kind of going to be a big deal, by the way. Any question?
That was what the question was going to be. What's the importance of radioactivity?
The importance is that, the question was, what's the importance? Everyone just assumed that things work this way. They never were able to measure it. So we're the first people to be able to definitively say, this is exactly what happens. And so I might not get quite in science or nature, as you know the importance of that. I may not quite get in science or nature just because it's already been assumed that this is, this is how it works. But I think there's a good chance I might still make it. Anyway, other questions? Anyway, okay. All right, I'm babbling, so let me just go on to stuff that actually matters. And
somehow related to life in outer space, you'll get into science or nature. Just a little sentence that says, this is why this will help us determine life in space.
Science and nature, they're definitely friendly to geology. I've noticed that. And I like that. I kind of like reading geology. They're friendly to chemists. They're definitely, I mean, science or nature, they're definitely friendly to biochemists. That's their number one. That's their like bread and butter. But, whatever. So I'm not a biochemist. So I have a hard time getting in there. Especially if you solve the structure of like some kind of protein complex, then you definitely got yourself a science or nature article. Anyway. So, let us finish up this wonderful class with the liquid mixtures. Not my favorite subject. I mean, let me just be very honest about that. What am I going to put on the final? You're going to know when I do the review. Because I don't really know where I'm going to go with this. Because I've kind of run out of time. Largely run out of time. And what that is all concerned about is how volume changes with number of moles of the substance. And again, I'm going to be friendly, and I'm going to keep pressure. Excuse me. I'm going to keep pressure constant. I'm going to keep temperature constant. And I'm going to keep number of moles of the. Be careful with this. Of the other thing. Write this down. Don't get this wrong. All right. I'm going to talk about changing a volume of a liquid with the substance A, given that there's a certain number of moles of B. Okay, so that's what I'm talking about. Now, excuse me, this is kind of tricky. Excuse me. Let's say I have 18 grams of H2O. Okay, now 18 grams, that's a special number. That's 1 mole, right? Now, if I add another 18 grams, how do I want to put this? I'm sorry to kind of write over your notes. All right, so I have a cup of water. I have 18 grams of water in it. I'm going to add another 18 grams. And that is 18 milliliters per mole. All right. Excuse me. Now, if I have ethanol, then the change in volume per addition of water, given that pressure and temperature are constant, and B, okay, so this is my dream. Oh, sorry, dream. I'm talking about throwing up in a liter, in an ocean of ethanol. All right, pure ethanol. And I'm adding, okay, pure ethanol, but I'm adding water to it. And that's 14 milliliters. Okay, so that's my point. So what happens is that when you have essentially a square hole, when you have a square hole in a round peg, it doesn't fit. And because it doesn't fit, you don't know what you're going to get. And we're going to go over all the thermodynamics of all this, but this is kind of the idea that, yeah, I mean, the big picture of things, you know, I like the big picture of things. I'm already writing a question in my head on the final. And you should recognize when they do this kind of stuff, because I do this kind of stuff all the time. Big picture. Square hole, round peg, and they don't fit. And so the numbers don't match. nor should they. And why is that? Well, we're going to go over all the thermo of that. And let me calculate the actual volume. The volume is, sorry, that was ugly. We're going to go from, we're going to integrate an equation. Now, you should recognize that this is a partial, and then I've got NB as well. Otherwise, why would I care? I'm talking about making a solution. And this little hat, by the way, that means it's a partial. Partials have to be integrated. There we go. Yeah, there we go. Okay, now, damn this thing. You can actually find this in engineering tables, but check this out. It's tempting to say that these are constant. You actually kind of treat them as constant. Not yes and no. Let me explain and then de-explain. And I hate to be obtuse, but let's look at how the partial of volume of A, and I got this out of your book. Partial volume of B, again, I got this out of your book. I'm not trying to make excuses out of them. Kind of. And we're gonna look at the mole fraction of B. So that's gonna go from 0 to 1. Okay. And what happens is, okay, so this is the same notation. I'm not really drawing that very well. It works like this. Yeah. And yeah. Yeah, I'll make it perfect. And OCD. Anyway, it turns out that these are functions of composition, making this whole thing a real biz knocker. I mean, this is much more complicated than it looks. And that's why I'm trying to cover this stuff, because it really sucks. It's very complicated to explain. And anyway, now this is the damnedest thing, though. Where's my equation? The thing is, though, all right, so I've got my ethanol, I've got my water, and I'm going to mix them, usually about 2/3. That's where I like. Anyway, I'm going to mix them to about 2/3. Now, knowing my target, knowing where I'm going to go, means that these are already set. Right, I'm like here. If I'm here, I'm allowed to know that, meaning I'll give it to you. And any problem sets, excuse me, any problem sets, I'll just give you the partial volumes. And that's what these are called. These are called partial volumes. Oh, excuse me. And they're determined by the final composition. Now, the damnedest thing is, again, they are functions of composition, but they are determined by the final composition. Now, last time I checked, I am definitely going to mix about 1/3 rum with 2/3 Coke. And having decided that, I already know what these are. And so I can measure it. I can measure it and know it and not have to worry about it. So, again, I'm about here. That means that I can determine the final volume of the solution. Now, how does that work? All right, now, knowing that I can already determine the final volume of the solution, let me give you, excuse me, the equation that tells you exactly that. And, that's boring. That is this sucker right here. What I want to do is look at the difference in, excuse me, what I thought I should have measured versus what I did. And that is the change in mixing volume. Okay, now this is, again, excuse me, I don't know. This is, I should have measured 18 mils upon 1 mole of water, but I didn't. I should have, I didn't. And how that works is going to be the sum of all the damn things that I added, which is the molarity of the number of things I add, which is an easy thing to calculate, versus, God, where am I at? Okay, now that's the partial volume minus okay, and what is the M sub I? The M sub I is pure substance. Okay, now again, I'm adding a lot of water, not my case, a lot of ethanol to a lot of water. Now, I know how much ethanol ought to add, but I'm going to add water to it. It's not going to be the same thing. I measured the difference. Here we go. That's what we get. And, what do I want to say about that? Oh, my God. You can measure all thermodynamic quantities from that, and that is that you can measure Gibbs, the change in Gibbs energy per mole, and let's keep certain things constant like temperature and pressure. And N sub I is not equal to, and now this is kind of complicated. N sub I is not equal to N sub J. J is your other guy. I is your guy, J is not your guy. Okay, you have to keep that straight, because that's going to be on the, I'm going to send a problem set, and you're going to see that. Okay, so anyway, that's how to keep this straight. So anyway, do things want to change? Do things want to change? This is either negative or not. Yes, things want to change. Things want to mix. This guy is going to be negative. This guy's going to be negative. And that's why things change. We know that, all right? And we can also do this. We can do enthalpy. And let's think about our guy. Our guy is going to be I, and that is the change in enthalpy. You don't really even have to write this down. Handwriting not good today. Anyway, so we can think about enthalpy changing. Now we know that when you mix two things together, they often get warm. Not always. Sometimes they get cold, but that's rare. But this is what it is. It is what it is. And we can also think about that because of the heat capacity. At constant pressure, because we're in a constant pressure world now. I'm not going to screw you guys over on that. And that is the change in the heat capacity of substance I with said dilution. And I'm writing the same thing down so you don't have to do that because it's kind of stupid. Anyway, there you go. Okay, you can imagine where we're going to go with this. I'm going to go with this places you don't really quite think, so you might want to write this bit down. let's do entropy. Entropy of substance I is going to be the change in its entropy with dilution. That's how I'm reading this. And we're going to keep temperature and pressure constant. And NB is not, NI is not equal to NJ. Otherwise, that doesn't really make a lot of sense. Now, this is where this gets kind of clever. Okay. This is where this gets, excuse me, this gets kind of clever. This is minus, I just want to remind you of what we've gone over. This is minus dg dt at constant p. N sub I is not equal to N sub j. Okay, there you go. Now, don't forget this stuff. This is the second test material. Now let's do another one. V sub I is, now I've already gone over this, the change in volume with at a constant temperature and pressure. And N sub I is not equal to N sub j. Otherwise, why are we doing this? That wouldn't be interesting otherwise. And this is the change in G with respect to pressure, constant T, not constant V, constant P, and N sub I is not equal to N sub j. Okay. So, anyway, basically, you know, we can reformulate all that thermodynamic crap that we went over with in the second test. We can reformulate it in this extent. And what ends up happening, I'm not even really supposed to tell you this, by the way. Why do things not mix? Now, I'm supposed to go over why do things mix? And I'm not going to do that, because it's more interesting when things don't mix. Why do things not mix? Why can I not mix hexane and ethanol? Actually, hexane and ethanol actually mix. I should be careful of that. Anyway, hexane and water don't mix. Why do they not mix? It turns out that it's this bastard right here. Turns out that the enthalpy of some things not mixing is highly, highly positive. Not good. Not good, said the cat, right? Now, you don't want this to be positive. You want it to be negative. And it's not. And because of that, hexane and water don't mix. And remember that's because we live in a world not at constant entropy and constant pressure. We don't live in that world. We live in this world. Constant temperature, constant. But anyway, you get the point. Anyway, we live in a world of constant temperature, constant pressure. And that means that delta G gets to decide everything. Now that means that if the enthalpy of mixing is positive, then that's a loss of entropy. That's this, you know, heat has to go into the system. And where the hell did that heat come from? Well, whose engine got burned? Right? Someone's engine got burned when enthalpy went into the system. And it sucks. It doesn't work. It hates it. So it doesn't do it. So anyway, at the same time, things do mix. You can usually think, this son of a bitch right here, this guy is actually very friendly towards things mixing. And it likes to push things into solution. And this guy tends to fight it. Anyway, I thought that was kind of, you don't care. Anyway, all right, so let's go over some other BS. Let's define whether things mix or not. Okay, mixing G. Why do things want to mix? And that is the chemical potential of something minus that something in its pure state. Okay, now that's ethanol and water, and that's just water. All right, so that's how things get pushed into doing things. Okay, and this is equal, now I've already done this, but I'm going to do it again. This is going to be the partial Gibbs energy minus the Gibbs energy. Okay, again, the way to read this, in case it's not clear, this is the Gibbs energy of a chemical in its pure state. So that's water. That's a cup of water. This is the Gibbs energy of the damn thing in the mixed state, weighted by how much is actually there. Anyway, so yeah, I hope that's clear. And
Where do we get G from? Is it, we're always working with delta G.
yeah. So the question is, where do you know? Where do you get any of this information from? Experiments. I don't really have good answers. That's why I cover this last. I have to supply all of this information to you. When I ask you test questions, I have to supply the information to you on all of it, because there's no other source of information. Now, physical chemistry, what we try to do is we try to figure this kind of crap out. We try to figure it out based on, give me the tell me about the molecule. Tell me its shape, tell me its charge, tell me, its atomic composition, tell me everything about the molecule, and if you tell me everything about the molecule, all of this will be calculated. Can I do it? No, not even close. We are so far away from being able to do this based on molecules. That's where we stand. And that's kind of sad, because if we could figure that out, if we could figure out everything, did I just say that? If we could just figure out everything, then we would know how chemical reactions would occur. We would know whether things want to mix or not. We're discovering all kinds of new materials all the time, and we don't have a clue how they're going to react. And if we had that, we could figure out ahead of time, like, is this a good battery? Right now, I mean, we hired a new guy, Jordy Cabana. Jordy, he hasn't taught any classes yet. He's going to. Jordy's job is to build new battery materials. And he's just straight up just discovering new substances just to do that. He discovers new substances, he puts them in a battery, and he sees whether that shit works or not. And he doesn't have a clue how it's going to come out. And that's kind of cool, because that's how we do things. So anyway.
So we're going to expect an explosion from SES?
Hopefully not. But let me just, all right, and you guys are wanting to leave right now. Let me just go over two things, because this connects back to what we covered before. Now let me go over that. Again, all of this works the way that we have covered before. I don't want you to forget that, all right? It's important. And that means that if you look at the way things change, handwriting suddenly got better. Okay, a partial. Don't forget this. Oh, this is so on the final. A partial makes no sense. Well, this is part of another partial, or it's integrated. I told you this a long time ago. I miss you people. And I hope you do well in the 343. It really means something. Okay, now this is equal to the volume of mixing, and minus, because I'm on a roll, let's do this. I know that, now here's how I know this. Here's how I know this, so that you're not lost. I know that the conjugate of P is V. I know that. PV equals nRT equals energy. That's how I know that. TDS. TDS. I saw TDS. I got sick of TDS. All right, there's a minus sign, whatever. Half credit, right? Full credit, whatever. TDS is energy. dG, dt, S. They're in the same room. They always have been. Anyway. Okay, I'm rambling now. Next Wednesday, I'll have your third test. I have no idea how it went. We're going to grade tomorrow. I'll have all your grades available for you then. It means nothing because I just don't know how this is going to go until your third test. So, folks, come to me. Come to me if you are short of points or something like that. One of you approached me today and said, hey, I'm short of points, so do that, all right? I have nothing else to say. I'll see you on Wednesday. I'll see you on Friday. Well, sure, but don't.